In this video, we will be voyaging to a culture and time period right at the beating heart of mathematics. We will be critically examining some of the most influential mathematicians of this time, and then we will be carefully investigating the insights and discoveries they left as their legacies. However, this isn't the usual story. This video is not about Newton, Euler or Gauss, three of the greatest European minds since the Enlightenment period. Moreover, this video isn't about titans of the ancient Hellenic world like Pythagoras, Euclid or Archimedes. In this video, we are going off the beaten track to explore an altogether different but arguably equally as influential and fruitful era of mathematics, the Islamic Golden Age. To understand why the Islamic Golden Age was so significant in the history of maths, we first need to understand the context of the world at the time. For centuries, the ancient Greeks had bravely forged a path through mathematical discovery. This started with thinkers like the early Pythagoreans in the 6th century BC and continued through to later Greek mathematicians such as Apollonius of Perga. Apollonius was producing his highly sophisticated work on conic sections in around 200 BC. This was right before the fall of the Greek Empire in the 2nd century BC. After this time, Rome became the dominant force. Maths was going through a fallow period here. It's not an exaggeration to say that Roman mathematicians couldn't hold a candle to their Greek predecessors, and this was reflected by a real sparsity of mathematical discovery. From this time onwards, maths in Europe continued in turmoil, leading on from the fall of Rome into the so-called European Dark Ages from around 500 AD. The bright flame of discovery, which once illuminated the vast cosmos of mathematics, had now been extinguished in the West. It was time for a new powerhouse to rise and take up the mantle of mathematical revelation. With the stage perfectly set, the Islamic Golden Age began in earnest in the 8th century AD. One key moment was the founding of the House of Wisdom in Baghdad, Persia. This, of course, is the capital of modern-day Iraq. Founded and funded by Caliph Harun al-Rashid, and inspired by early Islamic ideals of education and an emphasis on the importance of acquiring knowledge. It's certainly not an understatement to say the House of Wisdom was the thriving nucleus pushing human understanding forward throughout the entire Islamic Golden Age. The House of Wisdom was established not only to be a cultural centre for mathematics, but also for astronomy, alchemy, philosophy and medicine, with additional functions as a library and a centre of translation for the Islamic Empire. Translation at the House of Wisdom was indeed a vital function, because the work of Islamic mathematicians of the time began with materials they had collected from various other cultures. Poetically, the works of ancient Greek mathematicians were translated into Arabic at the House of Wisdom, which has been acknowledged as comparable to the ancient library at Alexandria, one of the marvels of the ancient Greek world. It's widely understood that Arabic scholars had a deeply held admiration for the works of the ancient Greeks. Translation was not only produced from the work of the Greeks, though. The Islamic mathematicians adopted the Indian positional decimal system. They also used Egyptian-style reciprocal fractions. Indeed, academics at the House of Wisdom were not overly picky with their source material. They showed a strong interest in assimilating scientific knowledge from many past civilizations. This was of great benefit to the history of mathematics, as many classic works of antiquity that might otherwise have been lost were translated into Arabic and therefore preserved. All that said, the Islamic mathematicians did make highly original progress of their own in many areas. In the rest of this video, we will go on to critically examine the work of a handful of the most distinguished mathematicians of the Islamic Golden Age. We hope to gain an understanding of their key insights, as well as the significance of their work when framed against the wider history of mathematical thought. Towards the beginning of the Islamic Golden Age, the 9th century, one of the most influential figures in the House of Wisdom was Muhammad ibn Musa Al-Khwarizmi, usually just shortened to Al-Khwarizmi. Many Europeans, though, will be more familiar with the Latinization of his name as algorithmi. This gave rise to the modern word algorithm. Al-Khwarizmi was demonstrably a powerhouse of his era. He first produced his highly influential and imposingly titled Book on Addition and Subtraction. This was based largely on the work of Brahmagupta, an Indian mathematician from the 7th century AD. It's interesting to note that Al-Khwarizmi made no claim to originality when he used a Hindu-sourced numeral system in his work. Nevertheless, he was still pioneering in a sense here, as Al-Khwarizmi's work on arithmetic was responsible for popularizing the Arabic numerals, based on the Hindu numeral system in Indian mathematics, to the Western world. Accordingly, Al-Khwarizmi was directly responsible for the adoption of the Arabic numeral system that is still used across the globe today. Despite the huge significance of this work, developing ideas from Indian mathematicians and their work on arithmetic was definitely not Al-Khwarizmi's magnum opus. Rather, he made monumental strides in the field of algebra. Al-Khwarizmi's most influential work was a book detailing rules for solving quadratic equations, amongst many other problems. Perhaps indicating its significance, the very term algebra comes from the Arabic title of Al-Khwarizmi's book, which was often shortened to simply Al-Jabr. In his seminal work, Al-Khwarizmi's systematic algebraic solutions for quadratics represented a huge development into the generalizing nature of maths for the Islamic mathematicians. Indeed, it has been said that Al-Khwarizmi's logical geometric framework for solutions was revolutionary at the time and palpably Greek in nature. Continuing on the theme of algebra after Al-Khwarizmi, subsequent Islamic mathematicians combined methods developed by the ancient Babylonians with the Greek system of geometry, creating a potent Islamic system of algebra that was based around proof. We can clearly see mathematicians in the Islamic Golden Age synthesizing previously held ideas, taking the understanding of other cultures before driving the limits of perception even further. This trend of using previously discovered mathematics was to continue as the Islamic period progressed, with a mathematician by the name of Al-Uqludisi writing a book of chapters on Hindu arithmetic in 952 AD. Al-Uqludisi is particularly noteworthy because he is credited with driving forward understanding of the decimal place system, even suggesting his own decimal point sign. Al-Uqludisi's system used an apostrophe-style dash above the units column in a very similar fashion to the decimal point we use today. Al-Uqludisi is also hailed as the first Muslim mathematician to write about the decimal fraction, well in advance of his innovative and much better known successor Al-Kashi almost 500 years later. The use of the Indian positional decimal system was later extended by another mathematician, Al-Samawal, expressing the square root of 10 to an astounding 6 decimal places. Whilst the decimal system was certainly not an original invention, the Islamic mathematicians of this era can again be seen to be making new steps with it. As we continue through the Islamic Golden Age, we will next encounter another mathematician at the foremost reaches of discovery, Omar al-Khayyami. In the 11th century, perhaps the zenith of the Islamic Golden Age, a range of new insight was provided by Omar al-Khayyami. He goes down as another of the most influential thinkers of the Islamic Golden Age. He made significant headway in the field of binomial expansions. This was to such an extent that in modern-day Iran, they still refer to Pascal's triangle, as we know it, as Khayyam's triangle. Al-Khayyami treated coefficients in his equations as specific numbers, not as lengths of line segments like the Greeks, and this helped to close the gap between numerical and geometric algebra. With regard to these sort of developments, it should be understood that although Arabic algebra had much in common with Greek geometry, the arithmetical part is alien to Greek thought. This shows the significant strides that were made in the Islamic Golden Age by thinkers such as Al-Khayyami. Further progress was made by Al-Khayyami in the realm of solving cubic equations. Notably, he was aware from his knowledge of Greek mathematics that certain geometric problems, such as doubling the cube, could be found by solving the intersection of conics. Al-Khayyami applied a systematic method of thinking, typical of Islamic mathematicians at the time, to demonstrate solutions for 14 kinds of cubic equations in this way. This can be understood as similar to Al-Khwarizmi, who classified quadratics into 6 types before producing methods to solve each one, whilst also illustrating the increasing depth of understanding of the Islamic mathematicians as the centuries progressed. This approach to the problem of solving cubic equations, namely using intersecting conic sections to solve cubics, had earlier been used by Greek heavyweights such as Menachmus, Archimedes, and also the Islamic colossus Hassan ibn al-Haytham. However, Omar al-Khayyami made an important original contribution when he generalized the method to cover all third-degree equations. Having discussed arithmetic and algebra, we can now venture into a third immense field of maths, trigonometry. Trigonometry first came to the Islamic world by means of India. There were influential works from as far back as the 4th century AD from India, but the Islamic mathematicians benefited from access to both Greek and Indian thought. In particular, Greek geometry of chords, as found by Ptolemy, and Hindu sign tables. The earliest of these tables, surviving for posterity, features the sine function evaluated accurately up to 4 decimal places. Only the Ptolemaic chord and the Indian half chord were known at the beginning of the Islamic Golden Age, but the Islamic mathematicians developed further trigonometric functions from as early as the 9th century. These further developments did not stop here, though. Mathematicians such as al-Biruni and al-Wafa made great steps forward with regards to spherical trigonometry. In his most influential work, Al-Biruni observed that contrary to earlier thinkers, the sun's highest point in the heavens was in fact mobile rather than fixed. This discovery could perhaps be seen to pave the way for the likes of Johannes Kepler and his work on elliptical orbits. Much in the same spirit, Al-Wafa's trigonometry assumed a systematic form. Al-Wafa was the first to provide and prove double and half angle trigonometric formulas. It is prudent here to note that in the Islamic world, the calculation of spherical triangles was necessary to carry out ritual customs, so the work of both Al-Biruni and Al-Wafa was regarded as highly significant at the time. A final thinker that we will examine is Jamshid al-Kashi, a noteworthy mathematician at the very end of the Islamic Golden Age, the 13th century. To this day, in French, the cosine rule is named Théorème d'Al-Kashi, as Al-Kashi was the first to provide an explicit statement of the law of cosines in a form suitable for triangulation. This should provide some insight into the grandeur that Al-Kashi's name carries, but he is acclaimed even more highly as a significant thinker in the history of decimal fractions. Al-Kashi's breakthrough in this respect was in using decimal fractions not just for approaching algebraic real numbers, but for irrational numbers such as pi. Al-Kashi had a particular strength in long, rigorous calculations, which can be seen in his incredibly accurate approximation of pi. This was beyond anything that had been seen before, at a monumental 16 decimal places. Al-Kashi's remarkable result achieved this level of accuracy by his calculation of the perimeter of a regular polygon inscribed within a circle with 3 times 2 to the power of 28 sides. Incredibly, Al-Kashi's computational tour de force was not approached in Europe until the 16th century, around 200 years after his death. Al-Kashi's approximation for pi was given in sexagesimal form, a number system working in base 60 rather than base 10, which was popularized by the ancient Babylonians. Al-Kashi then converted this to the enduring base 10 decimal form that we would be more familiar with today. This should be seen as a good example of Al-Kashi's willingness to draw from different cultures and systems, choosing the most effective techniques. In fact, on a wider level, this is further evidence that from beginning to end, the Islamic Golden Age of maths was a true melting pot of ideas drawn from other cultures. This should be appreciated whilst not neglecting the highly significant developments made by the Islamic mathematicians themselves. In conclusion, I hope you've enjoyed this video as an in-depth critical examination of some of the most influential thinkers of the Islamic Golden Age. From Al-Khwarizmi to Omar al-Khayyami through to Al-Kashi, I hope that you've been able to gain an understanding of one of the most incredible eras of mathematics. Perhaps you've come away with a heightened appreciation of the mathematical culture encapsulated by the Islamic Golden Age, as well as some of the people providing the impetus for key discoveries. Furthermore, I hope that this video has inspired you to think critically about cultures all over the world. If we look back through the history of maths, we see that cultures build on each other. Humanity is much greater than the sum of its parts, and ideas from around the world culminate to provide us with a much richer historical tapestry. Finally, I hope that you might be inspired to learn more about the many significant contributions to humankind that have come from all corners of the globe.